Hello friends, now we will discuss about physical concept of radiations. Okay, so this is the today topic. So here we will discuss about how a radiation occurs from a conductor. Right, so this is the fundamental concept of radiation in antenna systems. So now we will take a conductor with a cross section of something A. Right, so in this picture you can understand that I have taken a conductor piece with a cross sectional area, right? So for this is the conducting medium, and we can consider this is the metallic metallic piece of wire, and it is the cross section of the area. So for this conductor I am going to apply the electricity with the DC volt, right? DC volt, you know that DC volt we don't have any frequency. DC volt we have zero frequency. So we are going to pass this DC signal over here. So now the charge carrier will move around this area A. So it will pass towards the core, right? It will pass towards the core. If you pass DC signal, all the charges will occupy the center area and charges will move with uniform velocity, and in uniform velocity there is no further movement of or escaping of any charges towards outer side. Now I am going to increase the frequency range. That means I am going to convert from DC to AC. So I am going to change the source signal will be AC here, right? So if you apply AC signal for low frequency, if it is so, the charge will move around this cross sectional area. It will move further. Still it will move in the center part of the conductor, and there is no further movement from charge carrier from here to here. At the same time, if I move the AC signal from low to high, if we increase from low to high frequency, what will happen? The charge carrier does not flow inside the core. Instead of that, what will happen? The charge carrier may move towards inner to the outer conductor, right? So towards the outer conductor the charge carrier will carry, right? It will move further. So inside there will be a open space. Now where the impedance state will be high at the core of the conductor. So now the charge carrier does not move at the core. Instead of that, what will happen? It follows the inner part of the outer conductor. So around this conductor the charge carrier will move. Again, if I increase the AC signal further, what will happen? The charge carrier does not flow inside the conductor. Instead of that, it will flow outer surface of the conductor. Here it will carry. This effect is called as skin effect. It is a basic of radiations. Okay. So charge carrier does not flow in the core of the conductor. Instead of that, what will happen? The charge carrier will move around the conductor. That is the basic principle of the radiation part, right? Here I have given lot of diagrams. The one is curved structure, the another one is bent. Here it is truncated, it is improper terminations. Here we have two different dimension of wires, it is joined together, and here I have shown the radiation part, right? So these are also different kind of radiations. If you make the wire in this manner, right? If you bend the wire, there is a radiations. If you curve the wire, there is a radiations. If you truncated, there will be a radiations, right? If it is not properly matched, the signal will be escaped, right? And here if it is two different diameters are joined together, and you have some disturbance at the point, right? So what is the summary of this case? If a charge is not moving, it is stagnant, current will not be created. No current, there is no radiations. But here what is happening? The charge is moving with uniform velocity, still there is no radiations, right? The charge is moving with uniform velocity, that is occurred at DC, pure DC, as well as very low AC signal. Instead of that, what will happen? The charge is moving with different velocity. What will happen? Now we can raise the question of radiations, right? The radiation starts occurring, right? If the charge is oscillating in a time motion, it radiates even if the wire is a straight. Clear? You have a straight wire, but I am going to apply high frequency. So what will happen? There is a chance of radiations. So these are the different kind of radiations in a single wire. Now this is the basics of antenna radiations. Here we have generator, and this is the transmission line. The transmission line is tapered at the end. Okay, the tapered section is used to match the impedance in the free space of 377 ohms in order to make the spherical wavefront to the plane wavefront, and this is the corresponding field components. So this blue color field component is the electric field component, the red color is the magnetic field component. Both are perpendicular to each other. So now this is the clear diagram of the antenna radiation in free space. So this is the transmitter, transmission line. The signal is transmitted over here, then it creates or forming the electromagnetic signal over here. So here up to this for some extent the wave becomes spherical, and then this is the plane wavefront. The plane wavefront will be the perfect transmission of electromagnetic signal in the free space, where the impedance will be properly matched with the free space impedance, right? And now the basics of antenna, right? We know how to create a field component. We have plate number 1, this is plate number 2, and we have space between the plate 1 and 2. The plate 1 is connected with high positive potential, plate 2 is connected with negative potential, and what is happening? Because of the medium, the field will be produced. Okay, the electric field will be produced from positive plate to the negative plate. So this is the basics, fundamental of antenna systems, how the field component is fringe out. Now I am going to just relocate these plates, right? I am going to connect positive plate over here, negative plate here, right? So I am going to connect high positive potential for the first plate, and this is I am going to connect high negative potential over here. So what will happen? The electric field will start fringing out from positive to negative. So just I am going to relocate this positive plate over here and negative plate over here, then I am getting some field component. This is the fundamental of antenna radiations. See here, this is the dipole, right? This is the positive polarity, negative polarity. See how the field component is produced from positive to negative. So this is the direction of field component. And see here, because of AC signal, the positive and negatives are relocated. So how the field is produced? Field will be produced always from positive polarity to the negative polarity. That is very important. And what about the magnetic field? Magnetic field is always perpendicular to the electric field components, right? So these are the field components produced in the smaller dipole antenna systems, right? So now we will discuss about how a transmission line will act as a proper radiator in this case, right? See here, before proceeding all these things, these are the important relations of these voltage standing wave ratios and reflection coefficients. This is a small recap of your previous classes. So the first equation is voltage standing wave ratio related with the reflection coefficients. So it says about the minimum VSWR is equal to 1 if there is no reflections, right? If no reflections, reflection coefficient will be 0 and you will get 1 by 1, so VSWR value will be 1. So if VSWR is 1 for any system, it says about the perfect matching. So your reflection coefficient, the minimum value will be 0, that says if no reflections. If there is a maximum reflections, your reflection coefficient will be 1. So reflection coefficient will always between 0 to 1. Whereas in the case of VSWR, always between 1 to infinite, right? So these are the relations about VSWR to the reflection coefficients. Now here we can relate reflection coefficient with the impedance, right? So this is the load impedance, this is the characteristic impedance, and then we can relate the voltage level with the VSWR value. So VSWR is equal to Vmax by Vin. So all these informations are very important for maintaining the impedance mismatching should not occur in any communication systems, right? So now we will discuss how a transmission line can be converted into an antenna. See, this is the transmission line we have, and now here the output end is just left out without any proper terminations. So if it is left out without any proper terminations, what is happening? The radiation is insufficient because it leads very high impedance state it becomes infinite ideally. So how we can make a transmission line becomes an antenna radiator? Now we'll discuss over here. See, in these systems we have a transmission line. The terminal is just opened where impedance will be infinite. If it is so, if you put in these relations, reflection coefficients, what is happening? It leads very high reflections of 1. Now I am going to make this end is slightly flaring like this. That is the second picture. So if you flare like this, what is happening? At this end, your information is traveled over here, and because of this flaring, that it will be scattered like this. So because of this scatter, what will happen? The opposite direction of field components will be getting cancelled because whose current component will be opposite each other. It is cancelled. So only a portion of signal will be radiated, right? So this field will be parallel to this field. So this will be radiated, but it is not up to the mark. So only 50% radiation is possible. So how we can make it is fully radiations? We have to go for this complete perpendicular structure of the transmission line. So I am making this transmission line perpendicular exactly. So what is happening? This field component is parallel to now this. That is the same directions. So the field component will be added up. So we are getting a very good radiation field. Clear? So this is the basic concept behind this. So instead of leaving the terminal just like this, I am going to bend completely the end, right, perpendicularly. So I can add the electromagnetic signal, whatever is communicated from here. So their field component will be added up. You will get very good radiations, right? So this diagram shows about, and here this is the very high standing waves. It will be produced because it is not matched at the terminal. So the second diagram says about it is proper radiation occurs because the current produced at this terminal is parallel to this here. Is the idea clear? Right. So now this is the voltage distribution and current distribution of half-wave dipole antenna whose length is lambda by 2. And the blue color says about, blue color line is the current distribution that will be maximum at the middle, that is center of the antenna. At both ends the current will be 0 because the voltage distribution will be very high at both ends. See here, the positive and negative polarity at both end of the terminals are interchange because I am applying AC signal, right? So voltage distribution will be 0 at the middle, maximum at both ends, where current distribution is maximum at the middle, 0 at both ends. So this is the voltage and current distribution of a smaller antenna. So this is the respective diagrams, and yes, with this we will complete the today class.